SR latch. All right.
Let's just move on from that one.
So we talked a little bit about the SR latch, and wants to control. Well, the idea of this latch is we want to come up with a memory circuit so we can actually store memory, because that is required for a lot of our programs. So we talked a little bit about this SR latch, and it's two NORs, but the output is hooked to the input of the other NOR, which is very confusing at first. But hopefully we step through it. We'll step through it again, but this time via slides. So in this question, what happens, or in this situation, sorry, what happens when the set and reset are both to 0? Well, and this is important to start realizing, is you can set these as equations and start solving the equation to figure out what the answer should be. So I need like a giant pointing stick. So I guess I'll just use my mouse. Well, Q next, that's Q here, is 0, because that's what R is. Good morning. And plus Q naught current, the current Q naught coming in. But we don't know quite what that is. And we're knotting the whole thing because it's a NOR, so that's what Q next would be, equal to Q current. Oh yes, Q current. Because, oh yeah, why is that? No one knows. Does it actually tell you, or does it just make you pretend to know? It makes you pretend to know.
Because I said so.
Because it said so. Well, that's cute. All right. So let's ignore this right hand. Obviously, Q next needs to be what R is, which is going to be 0, plus Q naught current, what the current value of Q naught is, and that's what Q next is. Q naught next is 0 because that's what S is. ORing. By the way, that plus is an OR. Y'all haven't gotten to that yet, but we will. That's an OR. So 0 OR Q current coming up here, whatever Q current happens to be. So what they're trying to say is Q next is equal to Q current, and they didn't really give me a good explanation, but this next slide should. Or it does not at all. Wow, that's terrible. All right. So 0 or Q naught current. Well, that makes the 0 superfluous, right? Because it's an OR. So it's really just Q naught current, and then you're knotting the Q current. So if you knot the knot, it becomes Q current.
Right.
We'll be writing this all out, right?
Thanks.
And then Q naught next is equal, well, you just do the same trick, but now it's Q naught current. All right. All right. So this is how you actually store the values. Oh, because notice that Q next is equal to Q current and Q naught next is equal to Q naught current. So we've basically gone through a quick little proof mathematically to show that it's storing the values. What happens if set is 1 and reset is 0? Yes, I'm reviewing what we did last time. And that's because this SR latch confuses a lot of students. So, well, let's go back to our formula. Q naught next is 1 or Q current, and knotting that. Well, then we don't care what Q current is, because 1 or whatever is always 1. And so if you knot 1, you get 0. Okay, so Q naught next has to be 0. We do it the other way. Oh, 0 or, well, in this case, you have to have Q current. We know Q current is going to be 0 because we just calculated it right there. So 0 over 0, 0, knotting it as 1. So this is another way to prove or show that this is setting the latch. Of course, if you have set 0 and reset 1, to reset the latch to 0, it's the same proof as before, just in the opposite direction. I'm not going to go through this again unless someone needs it. We doing well? Good morning. All right. SR latches are memory. You can see the chain, little table on the side. 0, 0 is no change. 0, 1 is to reset it to 0. 1, 0 is to set it to 1. And then you can use 0, 0 to keep the value, and it'll keep outputting it. All right. I think we're doing well. Let's see, they're sequential. Notice that inputs to the next value could be either a 1. So the same inputs can yield different outputs depending on whether the latch was previously set or reset. This is the most important thing to keep in mind. Since it's a memory, the same inputs, aka 0, 0, may yield different outputs depending on the state of the SR latch. So the SR latch is holding state. Obviously, this is the simplest state because it holds 1 bit, but we got to start there. And this is very different than what we have been doing up to this point, because up to this point we've just been having a combinational circuit that runs through it and you have an output. All right, I told you last time don't ever do 1, 1 because that processes streams, which is bad. And what's going to happen if you do that? Well, both Q next and Q not next become 0, but this contradicts the assumption that Q and Q not are always complements. Here, let's show you what's going on. So if you set both S and R to 1, then that means, if you come up here to our formulas, Q next is 1 or, well, we don't care, so because we have a 1, so that makes it 1, nodding that is 0, so Q next has to be 0. S is 1, so that means we don't care about that, so nodding 1, it makes it 0, so Q next and Q not next have to be 0, aka this circuit. But now we have an interesting situation, because if after doing 1, 1, we then try and hold the value to 0, 0, then we're going to get 0 or 0, nodding that is 1, because R and S, we set them both to 0, and the previous state was both Q not and Q to be 0. So that evaluates both of these to 0, which makes them both not, and then Q next and Q not next is 1. But if these values go back to the Q not back to its own circuit because it's being fed back, then 0 or 1, nodding that is 0, same thing with the other one, and puts them back to 0. Hopefully you can see it's now going to flip and flop back and forth between 0, 0 and 1, 1, which is completely useless. Don't ever do that. But if you do get to that point in your simulator, you're only going to be sad. So that's what happens when you try and 1, 1 it. All right. How are we doing? So the next section of latches are basically a way to get around this issue, because you always want to guard against accidentally setting it to a state that's going to totally hose your system, because no one wants their computer to crash. Wait, does anyone? We might have a cybersecurity people that likes to watch their computer crash. All right.
It depends on what I'm trying to do.
If you've not thought yourself down the blue screen or something like that.
Blue screen?
But it depends on if you're defending the system or you're trying to take the system down.
Well, but the denial of service is the lamest attack in my opinion.
That is true. It's pretty lame.
All right, timing diagram. We haven't gotten to this, but this is kind of how a diagram looks when you're talking about the timings. Namely, when S goes from low voltage to high voltage, so you have the set to 1 and reset 0, then after some delay, Q and Q naught will slowly rise to their appropriate value of high voltage, or this one, Q naught, low voltage. We're going to go a little more into this later on. So if this doesn't make perfect sense right now, that's okay. Then if you move S down to 0, so you have 0, 0 and it's holding it, then you move reset line up, that'll reset the values, therefore making Q go back to 0 or low voltage, and Q naught going back to high voltage. You move reset back down so it's holding it, and then you can set it again, et cetera, in order to change the values. We'll be seeing more of these graphs coming up. But it is important to at least look or notice that there is a propagation delay between how long it takes from S rising before the gate saturates and changes the Q values. That's just important to keep in mind. And that's why we've been putting our delays inside of Verilog in order to signify how long it's going to be. Now, where do we actually get these delays from? Well, we talked a little bit over there about the number of gate delays, but how much time is that? That is going to be an electrical engineering problem due to your process, because you always look at how many nanometers a transistor is and also how much voltage is being pushed through. So the EE guy will go and tell you what these delays actually are. But we don't care right now because we're just architecting it. All right. Another very important slide, because no one wants to draw the SR latch every single time. And in fact, every time you draw a module, you don't need to draw the entire circuit. What we do instead is use a box, because we love boxes.
Oh, yeah.
Yeah, we do. So, and by convention, you don't have to do it this way, but by convention, you know, your inputs are on the left, your outputs are on the right, and you label inputs S and R and your outputs Q and Q naught. And what's nice is the more complex your circuit gets, the box diagram can just stay the same size. And then if someone wants to see what's inside your box, you can go look up what the definition is. Now, the proper symbols for an SR latch is where you do it like here, where you have S and R and Q naught. There's the N, or you do S and R, Q, Q with a naught afterwards. This both signifies that the output is Q and Q naught. Don't do this, because Q and Q naught is Q, and that is not what you mean. You'll get yourself confused. Okay, well, we talked about the SR latch. So let's go look at the S naught R naught latch. Hey, it's the inverse. So 0, 0 is now 1, 1, 0, 1 is now 1, 0, 1, 0 is now 0, 1, and what's the last one? 1, 1 is now 0, 0. But it's going to do the same thing. Because now we've changed it from NORs to NANDs. Do we find out that NORs and NANDs take, oh, that was just not. We didn't do a NOR. Okay, that's fine. So we have a NAND. So now we know that our 1-bit memory takes how many? Ooh, that's a good question. How many gate delays does it take to set or reset our NAND? Ooh. Or I'm sorry, or how many gate delays does it take to set or reset our S naught R naught latch?
I'm gonna say 3.
You're going to go with 3.
I'm gonna go with 3.
Why 3?
We have to do the initial. You have to get the Q, so you can use it on the second gate. Then you have to run that process. Oh well. Never mind. Maybe 2.
All right, let's take them one at a time.
Yeah.
Let's not do 1, 1 right now because it's confusing. Let's do 1 and 0, which is actually resetting it because this is S naught R naught. So if you have 0, or actually let's go up here. You have 1 going to this NAND. I'm sorry, I did it the wrong way. You have 0 going to a NAND. What's its value going to be? Well, the AND has to be 0 because it's a NAND. Nodding that is makes it a 1. So how many gate delays to go from R naught to Q naught? 1. Because it doesn't matter what Q is sending it. It's going to just take 1 delay to go over, no matter what, because R is 0. All right. Now, on the other hand, the set, on this case, it's going to have 1, but it's also going to depend on the output of Q naught. Well, what's the value of Q naught? Well, in order for Q naught to saturate to the correct value, because its previous value could be 1, but in order for it to saturate to the correct value of 0, you need to wait for that bottom NAND to complete, which means that's 1 gate delay before the top one gets the correct Q naught input, and then you would have 1 and, I completely blanked out for a moment. 1 and 1, whew, ending that is 1, nodding that is 0. So then the top Q takes 2 gate delays in order to get to the correct output on a reset. On a set, it's going to have the same situation. So far we're looking at 2 gate delays. What happens in order to hold it? Well, that's kind of you're not changing the output, so does it matter? It doesn't really matter. Not really. So we're going to go with 2. And 0, 0 is the avoid one because we're ignoring it. All right, do I need to go through this anymore? By the way, this dot means and. Anyone in discrete math right now? I'm sorry that the symbols are different.
It really messes me up. I started writing
That's
like
all
zeros and
that's
S's.
all I can tell you.
Yeah. I get them mixed up. I start writing zeros.
Someone also told me that she starts with 1 true and true, and I start with 0, 0.
Yeah, I do that too.
Yeah.
messed me
So
up
hopefully
on
that
the test
doesn't.
case.
Hopefully
I
that
was like,
doesn't mess
why
her
is this
up.
wrong? I'm like, oh wait, 0, 0, and I did 1, 1. Okay.
Yeah, maybe we should talk to her and see if we can agree on a syntax.
I'm just gonna do
Teach
it
their own.
the computer science way.
Okay.
I just gotta remember not to put zeros and ones and put T's and F's or whatever.
I mean, as long as you get the right result.
Yeah, that's true.
Right, it doesn't matter which one, but yeah. All right, so we have the S naught R naught latch, which is just the same thing as SR latch, just inverted inputs, and it uses NANDs instead of NORs. So it has a 2 gate delay. All right, we're now going to start our quest in order to try and get rid of the situation where we can go into a bad state by starting off with 1, 1 at some point or 0, 0. And the first thing we're going to do is add a control line, which means that the control line has to be on in order for any change to occur. So we'll have 3 lines coming in, and if control is 1, then it's possible to change it. But if control is 0, then it's only going to hold its previous value, no matter what you set S and R to. So, notice here that they have their S naught R naught latch that we talked about just now, but the control line is sent to a NAND. Why is it sent to a NAND? Well, if the control is 0, then it doesn't matter what S and R are, because 0 and whatever is 0, nodding that is 1. And so what comes here? Not 1 up here and 1 down here, which is, remember, in S naught R naught is the hold the line situation. The SR latch 0, 0 is hold the line, but in the S naught R naught latch it's 1, 1. So in that situation, when the control line is 0, it forces S naught and R naught to both be 1, which means hold the line right here. How are we doing? Okay. And let's see. So we have 1, which we want to change it. Then S and R are going to again be 1. Sending it to the NOT will then be 1, 1 again, because the 1 and 1 is 1, nodding that is 0. Wait a minute. No, I'm sorry. S and R is 0. Oh, I got that wrong. S and R is 0, so 1 and 0 is, of course, 0. Nodding that is 1. Same thing down here, and that's the no change. So you actually have 2 situations where you can hold the value. Although you actually have all the situations of S and R when C is 0 as well. So to reset it, you have R as 1, and that changes this one, the R naught to be 0, and set to be 1, which resets it to 0. And set is just the inverse. So you still have this situation where if you have S, C, and R all 1s, you get into the bad situation. But we're going to use this control line in order to come up with another circuit that'll get rid of it. Okay, so I went over this kind of fast. Does the circuit make some sense to you? What's happening? It's really just adding control line. What's the gate delay on this one? Three. Why is it 3?
Well, the initial part in the box part is 2.
Yeah, we've already decided the blue part is 2. And how long is it?
names should be acting in tandem.
Yeah.
So
That's just
overall
1.
delay of 1.
So it takes at most 1 gate delay for each of its inputs to arrive at the blue box. The blue box takes 2. 2 plus 1 is 3. All right. That's the easiest way to do this, guys. All right. Next comes the D latch, and this is where we'll finally come to the point where we get rid of the situation where bad things might happen. A D latch is based on the SR, but it has extra gates. So notice that the control line is still there, but the S and R are removed and they're migrated to a single line that says D. What's happening now is D represents the data you want to set in the SR latch, but you only set it if C is on. So C enables or disables writing to the SR latch, and D is the value you want to read and write. So D can be doesn't matter what, I'm sorry, if C is 0, it doesn't matter what D is, but if C is 1, then whatever the value of D is the memory that will go into the D latch. All right, how does this work? Well, real quick, let me bounce back. Notice that the difference, it's the same circuit as your SR latch with the control input, but now you have a NOT here. And what this does is it forces the D, what comes on top, to always be the opposite of what goes on the bottom because you're inverting it. Therefore, it's either going to be 0 and 1 or 1 and 0, which is good because that's what we really wanted. Your control line still controls if it's holding value, so no matter what D is, if C is 0, you're holding it. But if the control is 1, D is going to be 0, so D goes 0 and 1, which the AND of that is 0, dotting that as 1, so S naught is 1. And then down here you're dotting the 0, so it's 1 and 1, which is 1 dotting that 0, so you get 1 and 0, which in the S naught R naught latch is a reset. And then if D is 1, then these numbers are going to be flipped, and in which case if S is 0, S naught is 0, R naught is 1. Remember, it's a NOT latch, so that sets it to 1. The best thing about this circuit is you can no longer go into your bad input combination, so you're now guarded, at least on a circuit level, from messing something up. All right. Everyone got this? Great. So, what's the gate delay on this?
Well, let's see. It's going to be 4 because the inverter.
Yeah, the
adds
inverter,
extra
we
one to
pulled it with a NAND, so now we got 4. So, notice that there's now a cost for our protection. So if we just made everything a bunch of SR latches, its delay would be 2, but to add the protection scheme, it doubles the delay to 4, and increases the area as well. It's a trade-off, but it's one that's definitely made because you don't want your machine going down. Okay, we'll stop there because that's going to